Now, some other properties of functions that we can talk about is where they're increasing, decreasing, and where they're constant or not changing at all. So let's establish those definitions, look at this graph, talk about it, and just go from there. So we're going to let f be a function. A function f is increasing on an interval I if for any two values, x1, x2, in the interval I, as you move from left to right, that's what x1 less than x2 means. From left to right, the function's increasing. So when you look at f of x1 versus f of x2, when you move left to right, the value should be getting larger, and we represent it that way. Now, function f is decreasing on an interval I if, again, for any two values, x1, x2, in the interval I, when you move from left to right, the values that the function takes at x1 and x2 should be decreasing. So as you move from left to right, this value to the left is higher up than this value to the right, and that'll make it look like it's decreasing. And now a function f is said to be constant on an interval I if for all choices of x in the interval I, the value of f of x are all exactly the same. So they're all equal. There's no change whatsoever. Looking at this graph, we're asked to determine where the function is increasing, decreasing, and constant. So for increasing, we just find where it starts to go up, and we keep track of that. So from -4, that's the first x value for which it starts to come back up, and it just keeps going until you get to 0. Now, for particular reasons, and more specifically when you get into calculus, we're going to take intervals of increasing and decreasing to be open intervals. So we don't include -4 and we don't include 0 in this interval for where the function is increasing. Now, to figure out where it's decreasing, notice at -6, it just starts to drop down right away until we get to -4. And again, for various reasons, we're going to take only open intervals to discuss where it's decreasing. Then as you keep moving from left to right, there's no other spot where it's decreasing until you get to 3, our x value for 3, and then it just starts to slide down until we get to 6, and then it stops. So again, open intervals, we have two sets. We want to take the union of those two to make just one set out of it. Now we're asked to find where the function is constant, so that is the horizontal line right here from 0 to 3. So we can talk about where a function is increasing, where it's decreasing. Now we can talk about the peaks and valleys. First, we're going to talk about local phenomena. There's a couple typos. I switched it out. So let f be a function defined on some interval I, and let c be a number in I, right? Because grammar is important. So first and foremost, a function f has a local maximum at c if there is some open interval I containing c, so that f of c is bigger than or equal to f of x for any x in this open interval. The number f of c is called a local maximum value. On the flip side, we could talk about local minimums. So a function f has a local minimum at c if there is an open interval I containing c, so that f of c is smaller than or equal to f of x for all x in this open interval. The number f of c is called a local minimum value. Now we'll take a second to talk about why we care about open intervals in this sense. Let's say that you had some crazy curve like that. Now this point right over here it's essentially a valley in relation to everything else around it. So if this is on the xy plane, if we make an open interval around this number down here, and we look at what's going on in the plane with this dotted circle, essentially we're zooming in so that we have a picture that looks like that. And this is the minimum of just this local picture here. So if you covered up the rest of your graph and only looked at that picture down here, that's the local minimum. And so that's why we deal with open intervals here. This will make more sense on the next page when we talk about absolute. Looking at this graph, we want to find at what numbers, if any, does f have a local maximum. So we go around here. Nothing over here is going to be a local maximum because anything to the left is going to be larger. And so we have to wait until we get over to here where x is equal to 1. That will have a local maximum here. That is the highest point relative to anything near it. So what is the local max, or what is the local maximum? So that is going to be 2. Right? That is the highest value that the function takes, and it takes that value at x equals 1. Next, we want to find the minimums, the local minimums. And so likewise, over here, we have one at -1, and we have another one at 3. And we're asked to find what are the local minimums. So for -1, if you're just zooming in right around this spot here, the highest or the lowest that this function goes is +1. And over here, if you zoom in only on this section right here, the lowest it goes is 0.